Okay. Let's say we have. We'll just do this in 2 dimensions because green circuit works only in 2 dimensions. Now, the last 2 sections of the text, among other things, we extend Green's theorem essentially into 3 dimensions. And proofs of the theorems that we have there are really pretty challenging. But I'm not going to test you on the proofs. Just the ability to use the theorems because they're behind almost all electromagnetism and a lot of mechanics, especially fluid mechanics and so forth. You see some connections. Okay, so you got this function alpha of x y. Most authors use P and Q to the I and J components of this vector function. And we want to look at, well, I'm going to start with what's essentially a proof. It isn't terribly difficult to understand, but it's far from easy. Okay, you got a rectangle. And this is in the x direction, this is in the y direction. So rectangle with the sides parallel to the coordinate axis. And we're going to have a path that goes around this rectangle. Here to here, we're going to call this curve C1. It's a very straight curve, so it's easy to parameterize. Okay. And we're going to call this one C2. We're going to call this one C3. We're going to call this one C4. We want to do, well, okay, C. Which is C1 plus C2 plus C3 plus C4 means you just do C1, then C2, then C3, then C4. It's a closed curve. We want to do the line interval. I'm making many mistakes. One thing that we would have erased in the last 2 hours, but I'm getting a good start this time. Okay. We want the integral to the closed curve C. That's simply I could write this as f dot vector ds. But the vector ds is unit tangent vector times ds. We want to emphasize that we're taking the component of the field in the direction of the tangent, and the tangent at every point. Okay. And of course, this is equal. Integral over C1 of f dot T ds plus the integral of C2 over f dot T ds. So it's not right in the bottom, it's f dot T ds. Okay. But we're going to do it individually. It's going to turn out that this is equal to the double integral of partial p with respect to y minus partial q with respect to x. I think I might have that back, which we'll see in the process of the proof. With respect to area. Okay. We're going to more or less prove that for this rectangular region. Then I don't think your text does it. But show you how this extends down a simple closed loop. And it's not difficult to understand that. They draw a picture, makes that really obvious. Again, it's not trivial, but it's not really challenging. Not overly challenging, okay? Okay, well, let's look at what happens here. Okay. Let's just start with the dot T ds, okay? Over C1. Now, what's a tangent vector? What's a unit tangent vector on the curve C1? Okay. On C1, and it's in the x direction. It's a unit vector. What's a unit vector in the x direction? I. Okay. What's a unit vector in this direction? J. So it's really simple. Okay. Makes things very simple because then you can see the hard thing more easily. There's a hard thing involved. Not that hard. If you understand the definition of derivative. Okay. And I think we do. Okay, so on C1T is the I vector, it's obvious. Okay. Pause the video and somebody tell me what the okay, anyhow. F dot T is what? You trace it out with the finger, a single letter, we do. With F, what do you get when you dot F with I? Okay. Okay. Let's say. X naught Y naught. At this point, right? This point's going to be X1, Y1. Okay. Well, that tells you what this point and this point are. Everything's parallel to the ordered axis. Okay. So what would my limits in the integral be? Now I could parameterize this ds, right? You know, I could let it equal t and let t go from x0 to x1, but we might as well just integrate x0 to x1. Okay. Okay. Now you can work out the details. The details are pretty obvious. If the integral over C3 it's not. It's p of x, y, dx, but it's actually p of x, y naught dx, right? So this will be p of x, y1 dx. I'll put more on the board. They'll make one good decision. So the integral. No, that's the one right, C1, but that's not where I want to write it. Integral over C1. Maybe it's happening again, I don't know. Okay. Integral over C1. Equals negative of the integral not at one of p of x by 1 minus p of x y naught dx. Get all the signs right. Look at the parameterization. We both does look at parameterizations. You might want to look at what they do. It's the same thing I'm doing. Okay. Make it slide. This is your difference quotient between the value of p here and the value of p up here. Okay. Being the difference quotient, its limit as y1 approaches y0 is going to be py of xy. Okay. So I could say that this approaches py and xy as y1 approaches y0. Meaning that for a very small increment here, and that's what this really is. Small as we'd like to make it. Follows that p of x y1 minus p of x y0 is approximately equal to py of xy times y1 minus y0, which we'll call p of x py of xy delta y. So I can insert a delta y in here. And now I can write this as so this is the integral py delta y dx. Negative sign. Meaning I do have these after. Okay. I'll fix that. After we develop the other end. Okay, now let's stop and digest that a little bit. Integral C2, integral over C2, okay? You're in positive y direction. So that's going to be the integral of q of x y, because your unit vector is j now, is positive. So it'd be the integral of q of x1y dy from y0 to y1. And the integral over C4 would be a negative integral from y0 y1 of q of x0 y. So the integral over C2 plus C4 of L dot T ds is the integral of we can do y0 to y1 of q of x1 y minus q of x0 y dy. Okay. But this is just a numerator of the difference quotient for x change. So this is approximated by qx of x1 times delta x. Being a little vague because I don't want to put it something with a lot of extraneous notation. Trying to focus on the idea. So this sort of wouldn't make it in a mathematical journal, but with just a little change, a little more specific notation. Okay, it becomes the standard. Okay, so this thing in parentheses becomes qx of xy dx. When it's time to do what? Okay, approximately. Well, now. Suppose the integral over C now becomes the integral from x0 to x1 of becomes approximately integral from x0 to x1 of negative dy delta y dx plus the integral from y0 to y1 of px delta x qx delta x dy. So the limit of this expression becomes right about this way. Might be a previous step that I want to draw. Right over here. QX times delta X is just the approximate interval of QX dx. Okay. Over a small interval. Because what do? We get this interval, we break it up into small increments, and we do this in each increment, right? Well, if this increment is small enough, we only need one increment to get a good approximation. And we're gonna get that when we let delta X and delta Y approach zero. So the closer delta X is to zero, the closer this is to this actual interval. That makes sense? Now, this is, this goes back to why we break things down to I's and J's and try out partition our intervals and all that stuff. We got to see in the book. That's the way it's developed. That's the way it's always developed. That's why I've been stressing. So we can really understand it here, because understanding this theorem is the most significant thing you will have done in mathematics. Secondary only to the significance of the two theorems in the last one. But they all kind of make the whole picture go simple. Okay, so I'm waving my hands a little bit, but we've got to understand that QX delta X is approximately to the best. Okay, this would be the limit as delta X goes to zero. Well, this is the limit. Dy delta Y gets replaced by the interval from Y0 to Y1. dy. Just to make sure we see that all underline this. I'll underline this and say that in the limit, this. Give you this. I don't know. Okay. Now your book writes it out a little more rigorously. If you understand this and take a good look at what's in your book, it's going to bring a lot of stuff together for you. And you're going to understand the idea. The book is a little more rigorous, a little more specific than I want to be right here because it's your first look at it. So make sure you try to understand this. Especially if you expect to go into the field that uses this one. And the two fields most likely used in our electrical and mechanical class. At least half the class. Okay. Okay, well, that limit becomes negative interval dy dx. Well, to make it double negative. Plus the double interval. And I actually y. Okay. So translating all this literally, I get this. Well, the order of integration doesn't matter. Because we have a square in or a rectangular ring. This becomes a double integral over the entire region of Qx minus Py, and dx dy is just the area. You know, your delta x and delta y are just the area, but you know, we're taking the limit as delta x and delta y go to 0, so we become dx and dy. So there it is. Okay. And I haven't put the limits in the interval. Goes from x naught to x one, y naught to y one in either order. And this means, remember when I wrote this down, it's out, right, was the right order or not. I could have stopped to think about it because I know that you go up here and come down here, you're going to get a negative. And that's going to be the integral of Py. But since I still have whether I'm focused or not, whether I had yesterday brain fog or not, I don't take too much attention to the order of things. Okay. I write it down, I check it out. Or I design it. And then write it down. Okay. So, a pretty straightforward derivation, but exceptionally limits all this stuff and this approximation, etc. We got to understand differential and a lot of stuff from single variable calculation. So it's really worth the effort to understand those because it's maybe your last chance to really understand this stuff that you're likely to benefit from in your future courses. Okay. Because it might well be that probably the majority of engineers is their last math course. Well, this is differential equations in the general. Okay. You have the differential equations, you're almost done with the formal study of mathematics. Let me go to file. You got to use it. Okay. Well, that's Green's theorem. And it says that you can get the integral of this function over an area by doing a line integral around the boundary. Okay. This is kind of an extension of the fundamental theorem of calculus. Fundamental theorem of calculus says, okay, you integrate a function of a single variable over an interval. Assuming it's a well-behaved function, it's derivatives, and continuity, and all that stuff. I'm trying to summarize it here. We'll do the integral from A to B. Yes, I'll write it this way instead of little s and big S. We're going to confuse that big S. Okay. That makes sense, doesn't it? Because F is the antiderivative of its derivative. Okay, you just do the antiderivative. That's your familiar process for the single derivative. Okay. Well, integrate radial function with respect to s. Well, that's a conservative function. Okay. gradient of a scalar function is conservative function. Is exactly what conservative means. Well, conservative means path independence. The theorem that says that if you have a gradient of a function, it is path independent. And if it's path independent, it is a gradient. It's an if-only statement, and this is just then our picture that goes with this is got a path from point A, point B, and it doesn't matter what path you follow. Okay, so that kind of represents what you know about conservative functions. So in this sense, the scalar potential function, because this F is called your potential function, is a two-dimensional or multi-dimensional because it is in confined plane, right? Drawing plane, it works in any number of dimensions. So if you've got a 10,000 dimensional data set, and they're all over the place, and 10,000 dimensional data set, you can still do a gradient and still imagine something about what's going on and all that. So this extends the idea of an antiderivative of an integral and its relationship to antiderivative to any path in any space. Well, the path would be continuous with parameter, okay? And on the function out makes sense in that sense. Okay. So you see the form of this is very similar to the form of this, right? Okay, now we have this Green's theorem. It says the integral of integral of Ti plus Qj along a closed path to C. Right vector dot ds. So that you don't have every time you scale it, you guys, is equal to the integral over the region. I think we're both using D for a domain. Might be R for region, but I think D might be close to what it tends to be. Actually, to make sure my notation is going to be relatively consistent. Oh. Yes, now, this doesn't look exactly like this. But this says, we can actually make sure to put this on the left-hand side. This integral over an area is equal to integral rounded bound. Okay. And we're going to generalize that a little further with the two integral terms. Stokes theorem and the Divergence theorem. All right. Okay, this is why it works. Let's just say that we've got a region that looks like this. If it works in this region, for any delta x, delta y, it has to work on this region. And so here's a big curve C. I'll put up in rectangles. Small and light. on any rectangle. Okay, let's just take these two rectangles here. We're gonna go. Counterclockwise here, because we're integrating counterclockwise here. If we went clockwise here, we have to go clockwise and we. Okay, right there is the path that we would follow. This rectangle. Okay. Here's a path that we would follow for this rectangle. So it goes from here to here, to here, and then down. Okay, now I haven't drawn that down very well. I need more board space, and I'll draw it a little bigger. The point is, you go around this thing this way, and then you go around this thing this way on this side. You went this way to this interval, and you're going this way to this interval, and it cancels out. Right? So we just erase that little boundary. Now we've. So. To the extent it's true for any rectangle, it has to be true for this bigger rectangle. Okay. Well, it has to be true for that one. Then we can extend to this rectangle. And now we're here's where I cancel this up. So we got the interior of this bigger region, right? And we can keep going. We can come down here. Okay. Now here we might run into a little bit of a problem. Because we've got this, right? But then we've got a little segment along this boundary. So let me make this boundary green. So now we've got to follow this boundary for short segment. But then we go this way and we go this way and we come back here and this one gets canceled out, okay? And then, well, why not go along this path? Now along this path, this is almost a straight line, but it's part of the boundary, okay? And then we go from here to here along that boundary, then we go here and here, and we come back down and this one goes away. Okay. Well, and we can do it again, go along this is the part of the path. And then we go maybe up a little ways there and then once there, and then we go to the back. Well, every part of this grid from the interior is going to get canceled by the adjacent part, and the only thing that's going to be left is what's on the total boundary. Is that clear? Can we see that? Okay, so I don't need to go much further. Okay, I'm not, but I mean, I could erase all these things one by one, but if you see it, then you see it. If you don't see it, draw it yourself and cancel everything out. Maybe draw not quite as many little squares. And of course, we can take the limit because all these squares approach zero, so we get integrals rather than sums and approximations. We get exact. No matter how many little increments you have, cancel everything out except what's on the boundary, and you end up with an integral around the boundary, and it's got to be equal to the integral of what happens inside here, the area. Okay, because you're adding up all these little area contributions. Okay. Because again, to emphasize, the integral around any one of these boundaries is the integral of qx minus py on the interior. You take the average value qx minus py, take a sample point on the interior and multiply it by the area, you're going to get exactly the same thing you get. Well, you're going to get approximately the same thing you would get if you do a p dx and a q dy and a p dx and a q dy on the fourth side. Okay. So that's a powerful picture. And it sets around through more powerful things because the things we look at next week are going to be like flux integrals. Flux integrals have anything to do with what's going on in physics right now? And we have a rate of change of flux if you're induced in MS. Okay. if you have hydrodynamics, and your book does a nice job of talking about that, but hydrodynamics related to it. And the divergence. You're talking about fluid flows through the surface. If you get pretty complicated, like if you got air flows, it's air is compressible. It's complicated enough for water flows which aren't compressible, at least not much. Okay. That makes sense. So, you know, mechanical for electrical. Now for a lot of industrial engineering and other types of engineering, it's not particularly applicable. But learning to think at this level is applicable to everything, including things that have nothing to do with physics or engineering. Right? Now let's see. Think of the brain fog. Is this history class? Well, this is applicable, so I should have done it. Right? Yeah, maybe a stretch, but not really if you really understand history. I don't understand the people enough to really make that statement, but I made it anyway. Maybe I'm making it up. I think there's a connection. Okay. I could have said all that like past, but these are this is ideal. Big idea. An application of this theorem is that sometimes it's easier to calculate the line interval than it is the area. And sometimes vice versa. So, you know, I took a good look at the text. I didn't, I looked at the problem set in the text, I didn't look at the problem set. And what was fine because I had to log in again and I had something to do. And not a good reason to answer what was it. Okay. But I expect that you're going to see a number of problems where one of these intervals is easier to do than the other. So if you're given a vector function and a curve, set up the area interval, set up the line interval. If you have a well-chosen example, one of them is going to be a lot easier to do than the other. But you can conclude what the area interval is if you know what the line interval is, or you can conclude with the work interval, whatever your line interval is, if you can integrate over the area. It's very powerful. It's very neat too, but once you get a handle on. One interesting thing you can do is if you pick a P and a Q, such that QX minus PY equals 1 over this horribly complicated region due to some weird curve that goes in and out, and you get you all kinds of headaches trying to set up the area interval. What you gotta do is set up the line interval, which might be a whole lot simpler. And you just pick a Q and a P such that this is 1. You could let P equal 0, Q equal X. And integrate this XJ over this boundary and give you the area. It's extremely neat, it's extremely powerful. And if you don't find it just astounding, it means you're better off being an engineer than a mathematician. Okay. All right. As an engineer, you're still going to use it. And you use it better if you understand it. At least know how to use it, right? And then try to go a little deeper, I understand. Okay. Divergence and curl are real straightforward. But the book has some really neat descriptions. And I'm going to repeat them. I've seen them before, but I think mostly in this book. And I never saw them when I was living in this place. And we got these vague descriptions of water wheels and other things. But what divergence currently mean? Okay. So. Okay. We've already seen the Dell operator review the gradients. We can use it to do a cross product, even though the Dell operator isn't really a vector treated as a vector. You both have some insightful comments. They have a nice way of stating why this isn't really a valid operation, but we treat it as if it is anyway. Okay. It worked. And the versions of that is L.F. Now we're going to go to 3 dimensions. You can do divergence in 2 dimensions. It's fine. It doesn't feel defined in 2 dimensions. This really kind of isn't. But we pretend it is anyway. Then we'll use the determinant. Do the curl because we've got 3 components. We're using the distributed law. You should be able to use the distributed law to do the curl because a lot of times if you got several components that are 0, it's easier. So, and you know, this isn't the definition. But by the determined definition, this is what you have. It turns out to be equal to what? I times partial of expectancy of Q minus, sorry, I times a partial of R with respect to Y minus a partial of Z with respect to Q. So R, Y minus X. Then it becomes J times what? PZ minus UX plus A times make sure I get them the right order. QX minus QY. Okay. You agree? Okay. Well, make sure you get it right. Even if I happen to write it down wrong, but I don't think it is. Now, close to the definition of cross product. This is equivalent to the definition of cross product. So there's your expression for the curl. Not this. Curl of F equals 0 if and only if oh, something's wrong. Didn't have a QX. What happened? Put the QZ here. Okay. And then No, something's wrong with it. On J, you're gonna get BZ. And it's RS. That's not running. Oh, that is not that across. AY equals QX, okay? I think those are right. But if you write this out correctly, it's obvious that the only way this is equal to zero vector is if this is zero, this is zero, and this is zero. The only way this is zero is if RY equals QZ. The only way this is zero if RX equals PZ. And this one, QX equals PY, okay? Now they call this the cross partials test. I never heard of the cross partials test. So I looked at this book. Okay. I'm not sure why they do that. I can kind of see a logical reason for it, except that this is much simpler. Okay. The key is that F is conservative. If and only if the curl of F is zero. Okay. So if you've got an electric field, for example, and you got a formula for an electric field, and the curl isn't zero, then that electric field didn't arise from charge. Okay. Now, as it turns out, you get an electric field, what's called displacement current, which we're going to talk about quantum physics. Okay. It's not an electrostatic field. Okay. Magnetic fields. Okay. Are themselves curled. So we're going to talk about that. Okay. What this says is, well, if F is conservative, then it's a gradient. And it's easy to prove that the curl of gradient is zero. And you just write that out. Okay. The curl of a gradient would be like the curl of partial depth with respect to X, partial depth with respect to Y, partial depth with respect to Z. If you do that, partials all end up equal. But you just write it out. You write it out and you see that you're going to have like a FYZ and an FZY. And an FZX and an FXZ. And an FYX and an FXY. Subtract. Since the order of partials doesn't matter, just prove that. So write it out. It's easy to write out. And you can write it like this. All you gotta do is write out the partial derivatives. You can see that all of them come out zero. Okay. Proves that the curl of a gradient is zero. Conservative field is one that is a gradient of a scalar function. Big deal. Not hard to read, not hard to see. Very powerful. Okay. talk about the Laplace's equation next time. So if like the gradient of gradient. So. Actually, it's the divergence of gradient of f. And if you just write out what's the gradient of f, it's f xi plus f yj plus f zk. And then dot that with this, you get fxx plus fyy plus fcz. Okay. If this happens to be zero, you've got smoothest possible function. And there are all kinds of these things you can prove. You know, this function has all kinds of things to be proper. And in some sense, it's kind of a transition to complex variables, functional complex variables. Something that might well play a large role in your engineering. Probably don't study it in those engineering disciplines rigorously, but you've already seen it to an extent in your differential equations with the trial function e to the RT, and you get a complex value of R, and you get cosine theta, sine theta, and all that stuff. Okay. And then you see that you get two solutions to the differential equation, one being the real part, the other being the imaginary part, with solutions. The combination of these solutions is a general solution. Okay. Remember that. And it'll come back. It's in your curriculum. You're going to see it next year. Okay. So make sure it's there, because your life is easier. You get through it quicker. You get through your homework quicker. You understand it better. Okay. Okay. The idea of the curl is it measures the rotation from the vector field. Now, the first vector field I did, I don't remember what it was, but something like yi minus xj or something like that. Okay. If you were to draw that field, we look back at your notes, you see that field, you can see kind of tends to rotate. The field of straight current side. You get a magnetic field. It surrounds this thing in concentric circle. Vector gets shorter as you go further away. They kind of fall off proportionally with distance. And that's a rotational field. If you toss the book is just an analogy, you toss a leaf into water. Okay. If there's a whirlpool around, that's rotational velocity field. And that leaf is going to tend to spin. Close against the center of that whirlpool, faster it spins, right? So it's a measure of how much rotation there is. Whether it's an electric field or magnetic field, whatever, there's not going to be any rotation in the electric field that comes from the distribution of charge because those fields are conservative. So that's kind of a neat thing. Another thing is divergence. And of course, we've seen fields diverge, fields that a radial field is the example of a divergent field. Okay. Well, a divergent field, if I do an integral around the closed path here, it's going to be zero, really. Okay. The line integral will be zero around the closed path. The line integral of It's divergent field. Random circle. Would be zero because if it's a radial field, it's always perpendicular to the circular path. Okay. Gauss's law kind of tells you it doesn't matter if this is a circle or not. Any curve that encloses a distribution of charge, okay, is going to have, well, I'm not going to make the whole statement. Okay, what we really want to look at for a divergent field, though, is the flux. Okay, how much of the field escapes this circle or sphere? Okay, well, the flux. And at every point out here, you got a radial vector. Haven't drawn it all that accurately, but there's your radial vector, and here your normal vector. It's the integral of F dot M. When we did this, we did the integral of F dot T. We could as well have done the integral of F dot M. Got a few normal vectors here. I mean, they're going to be at every point. Okay. F dot M, well, the normal vector is perpendicular to the tangent vector. Always. Okay. Treated like if your tangent vector is cosine theta I plus sine theta j, normal vector will be sine theta minus cosine theta, sine theta I minus cosine theta j. And you see that also in linear algebra. Transformation matrix for rotation. The cosine theta, sine theta, negative sine theta, cosine theta. Okay. What this does it's a simple corollary to this. It's just the integral of qx plus py, because one of your components goes negative and switches. You know, your y becomes x, and your x becomes y. And you know, hand waving over that. Well, it turns out this is the one that changes sign. And you get this. And you can do that symbolically without even understanding this, but it's good to do it this way too. Okay. So the point is, because you can do this for increments. It's not really correct with any more than this. If it was. That's a problem. Py plus px, you get the idea. Okay. Have to do it in my head. Take the time to do that right now. Okay, but anyhow, there's simple corollary. And I have to write it out in detail. Be sure I wrote it out correctly. No problem, remember things I just put up together. And then if I use it a lot, I remember. Then of course, they like I had yesterday. I know how to get them and I do it wrong. So there's a danger in that. Okay. That's a lot of what you need to know about that root system. Want to get your feet wet a little bit with parameterizing surfaces because that's hard stuff for most people. First of all, let's give you parameterization. Put that surface. I think the camera was on when I wrote this down, but maybe not. So if we have x equals t cosine theta, y equals t sine theta, z equals t. And theta goes from 0 to pi, t going from 0 to 10, or a lot of hands here. What do you have? Okay, well, let's focus a little bit because it's kind of a really fuzzy confusion until we sort it out. You ought to recognize that as parameterization. A circle of radius t. If you don't, well, I gave you the leading question. What if t equals 4? Then I saw some circles started with paper, but not everybody. Takes a while to process this. All that familiar. Okay, 12 t equals 4, you get 4 cosine theta, 4 sine theta. And you just got to know that that's parameterization of a circle of radius 4. I've been telling you for a long time, make sure you get this parameterization done. And you got a big two-dimensional parameterization. Okay. It's fairly gentle by the way they introduce this. Then the way it goes to the integral, you've got an integral of parameter space and all that stuff. Kind of hard to understand. Okay, so what if t equals 4? Well, you got a circle. The XY plane, but of course your point is not in the XY plane. The point is units above the XY plane, right? Okay. You got a circle radius on the XY plane. What XY Z is 4 units above the point on that circle. Yeah, people does a nice job. Okay. Does a nice job with about everything. And I like it work. Although I do have my favorites. I'm not going to ask you to spend $300. Maybe get 3 books inside. Okay. Used to use a Bradley Smith books that I really like. The props are totally good. Sorry. Could you get a secondhand bookstore for peanuts, less than $10? Okay. But those things are buying up because nobody's actually buying textbooks and selling them the book side. I think it's a disadvantage not having this book. Okay, anyway. That makes sense. Okay, so you have for every t, you have a circle of radius t, and above that circle you go t units. What do you call the shape that you get? If we're trying to calculate the flux of some vector field through this shape, which everybody identified as it's very good. Then we're going to want this parameterization of the surface. Okay. That's all it is to it. And then we look at parameterization of the sphere. You know, that's not too hard. You still look at circles down here, and then how high do you have to go? Okay, you know, the radius is squared, and the radius minus x squared minus y squared. Okay, radius squared. I think, cylinders. The cylinders just have a constant limit on Z number, or actually for cylinders, you just don't have T's here because your circle doesn't keep expanding, you just have a constant number. If the cylinder has radius 7, you're gonna have a 7. It's still a T here. Okay, if you understand that much, you're off to a pretty good start. But you know, kind of try to scan the book a little bit ahead, try to get some of these ideas and pictures into your head. Will be very helpful to you.